Okay, what I want to do is a sample problem where we have something much more simplified than what we have for any of the problems that you're doing, but it helps demonstrate a concept and approach on how to figure out what happens to the center mass of individual objects when we know the center mass of the entire system has to be in the same place. So Kaylee showed me an example of this in class after everybody else had left that I really like. So I'm going to give full credit to Kaylee. Great idea. So what are we going to do? We're going to come up with a board on a frictionless surface, so it's going to be on ice, and then we're going to have a ball on top of the edge of the board. And it's just balanced, so it's not going to fall off. This is a 10 kilogram ball, and we're going to have a 10 kilogram beam as well. So we made this as simple as we can by having two objects of 10 kilograms. And we'll pick a length here. Let's pick something that's convenient. We'll pick 4 meters for the length of the board. And so now the question is going to be, what is the center mass of the system? And so we do an average of the center masses of the individual pieces. And so the center mass of the board is going to be halfway, so that's going to be at 2 meters. So 2 meters to the center mass of the board. And I'll pick this as my x equals 0 axis. And so now this is our center mass of the board. It's out at 2 meters. Center mass of the ball is at 0 meters, and so when you average those two objects together, the center mass of the whole system will be at a location of 1 meter. So here's our 1 meter for the center mass of the entire system's location. So the whole system given by this big, huge X. So drawing these systems out as things are happening is the most effective way to go ahead and attack these problems. So now what am I going to do? I'm going to move this ball to the other end of the beam. And so as it moves to the other end of the beam, since it's on a frictionless surface, the beam is going to go to the left as the ball rolls to the right. And so the ball is going to end up on the right edge of the beam to make this simple again. And so the key thing Kaylee pointed out is to look at the relative distances between the ball and the center mass of the system, as well as the ball and the center mass of the beam. And so we see that the ball relative to the center mass of the system now, the whole system, is 1 meter. So when this ball rolls over to the end over here, then the center mass should still be 1 meter away for the ball relative to the system center mass. So what am I going to do? I'm going to move my beam over. I know that my ball has to be 1 meter to the other side now, so I'm going to put this big X again for the center mass of the system. And we know that the ball is going to be on the other end of the beam, so the ball has to be 1 meter away from the center mass of the system. And so we go ahead and draw our beam again. And so now this is 1 meter from here to here. And we also know that the center mass of the beam has to also be 1 meter away, so this is another 1 meter chunk. So that tells me this must be 1 meter as well. And that puts us right on the original axis. So we have 1 meter to the center mass of the system, 1 meter from the center mass of the system to the sphere or the ball. And so as a result, this is 2 meters. So we've essentially shifted our beam halfway towards the axis. And so now the center of the beam overlaps 2 meters on the left and 2 meters on the right. But still, the center of mass now of the beam is at 0. And the center mass of the ball is now located at 2 meters away. And so we're back to the original situation we had here, where we have 1 contributor and 1 not to the summation equation approach to this problem. But by visually looking at this, it should sort of helpfully make some kind of sense.